Hey guys, I'm back again, and I'm going to try to show you a little demonstration on conservation of mass law. Conservation of mass law is something that we will use a lot in chemistry, so it's pretty fundamental to a lot of the things we do in here, particularly stoichiometry. Alright, so first off, I've got a marshmallow here, and I've put it on the scale. So let's take a look at what the scale reads. And the scale reads, it looks like 8.921 grams. All right, so we've got close to 9 grams of what's basically just sugar. Marshmallow is a sugar with a lot of air puffed in it. That's basically what it is. And we're going to try to roast the marshmallow, which is going to be a chemical reaction, and then see what happens to the mass. So we got what everybody has at home, right? Nice little Bunsen burner. We'll stick this in here. And whoops. Okay, so it's a little much, but that's okay. Hopefully it won't drip out of there. Sugar is actually very combustible, so is flour. So that's a chemical reaction that we call combustion. So we've got C6H12O6 is reacting with oxygen. All right, well, what are we going to do? We're going to take a look and see if the mass of this changed at all. Okay, so I lost a little tiny bit of mass right here on the stick. Not much though, it should only be a fraction of a gram. And let's turn the Bunsen burner off. Take a look at the scale. And the scale now reads, 8.003 grams. Alright, so what's going on with that? Well, what a lot of people would say is we burned up some of the marshmallow. So about a gram of the marshmallow, 0.9 grams, thereabouts, turned into heat and light. So it turned into fire, right? So we converted some of the sugar into energy, turned it into fire. And that's what people would say. That's 100% wrong. What happened is you couldn't see where it went. Some of the sugar reacted with the oxygen and turned into the invisible gases CO2 and water vapor H2O, and the water vapor is hot enough that you couldn't really see it. If we could have captured all the CO2 and the H2O that left while the marshmallow was reacting, we would have seen the mass before and after was actually identical. Chemists have known this for about 200 years. Real famous chemist by the name of Antoine Lavoisier was the first person to figure that out. And what he was really good at capturing any of the escaping gases from chemical reactions. So this is a law. It's not a good idea. It has no known exceptions in chemical reactions. If you take the entire mass before a reaction happens, the mass that you get after the reaction has to be identical. Okay? And then we'll get into the explanation for why that happens. Our explanation of conservation of mass law is done using atomic theory, but that's different. So atomic theory explains why the conservation of mass law actually works. Conservation of mass law is just mass has to be conserved, and that's it.